Hello students, in today's class we are going to study about how to draw the molecular orbital diagrams related to the topic of chemical bonding. So molecular orbital diagrams, a very important topic. And before going into the detail of molecular orbital diagram, we must remember that in case of atom, all the px, py and pz are degenerate in nature. That is, the three are having the equal energy, px, py and pz. But in case of molecule, the 2px and 2py are the degenerate, but 2pz is having the energy different from both of these. So remembering this point when we will be drawing the molecular orbital diagrams. So starting with this, first we must be knowing about how to write the electronic configuration in case of a molecule. Since the molecule is formed by the bonding also, so we will start with which type of bond is there. So starting with sigma 1s. The 1s orbital is going to form, SS overlap is going to form the sigma bond. And whenever there is a sigma bond, there is altogether the formation of anti-bonding 1s also. Then sigma 1s, anti-bonding 1s. Then after that, we will be writing sigma 2s followed with anti-bonding of 2s also. Okay, so in case of molecular orbital configuration, we will be following a bonding followed with the anti-bonding part. Now comes the case of pi 2px. And what we have discussed in the starting, that 2px is having the energy which is very much equal to that of pi 2py. Both of these are considered degenerate in nature in case of the molecule. Now after that, there is a term of sigma 2px equal to py, pi 2px is equal to pi 2py. And then there is a term of sigma 2pz. Then again, the case of pi antibonding 2px equal to pi antibonding 2py. And the last one, the last case is that of sigma antibonding 2pz. So generally we used to follow this molecular orbital configuration when we are writing the configuration. But a thing that has to be remembered along with it, a very important note point is the energy level sigma 2pz and pi 2px, pi 2py. Remember these three, sigma 2pz, pi 2px, pi 2py. The energy level get reversed. What you have seen in the above cases, pi 2px is equal to pi 2py, and then there is a case of sigma 2pz. But in case when I'm talking about O2, F2, and then Ne2, in these cases, when we are talking about these molecules which are having the number more than 14, so in these cases, sigma 2pz, then 2px, and 2py got the position. So these are reversed. Sigma 2pz comes first, and then there is a case of pi 2px and pi 2py. So in the case of O2, F2, and Ne2, these three has to be considered in a different manner as compared in the above. So the first configuration that I have wrote is up to the 14 electron, and then in case of O2, F2, Ne2, that is in these cases, we will be considering 2pz first, then pi 2px equal to pi 2py. But there is no change, dear students, in case of anti-bonding orbitals of 2px, 2py, and 2pz. Now, before drawing the diagram, also some very important things are, the first thing that you must always remember is stability. Whether the molecule is stable or not. The stability can be given as if number of bonding electrons is greater than number of anti-bonding. Bonding are those which are participating in bond formation and are having the lower energy. And the other are the anti-bonding. If bonding is having, the number of bonding electrons are more than anti-bonding, then the molecule is considered to be stable. Greater number of bonding orbitals. Then the other case, if number of bonding is less than number of anti-bonding, then in that case it is considered to be unstable. The third case that must come into your mind, that if NB and NAB both are equal, then again it would be considered as unstable. So molecule is considered stable only when NB is greater than number of bonding electrons are greater than number of anti-bonding electrons. Now the second thing, the stability can also be given in terms of bond order. Stability in terms of bond order. In the first case, I have given in terms of number of bonding and anti-bonding electrons. Now the other is in terms of bond order. So bond order is defined as bond order is equal to half of the difference between number of bonding electrons and number of anti-bonding electrons. So if number of bonding electrons is greater than number of anti-bonding electrons, then the bond order is going to be positive. And if the bond order is going to be positive, so in the other case, if it comes out to be negative or if it comes out to be zero, then how we can say that it is stable in nature? So for the stability purpose also, we must remember that the bond order should always be positive in nature. And the main thing, the other thing comes here, when bond order is 1, 2, 3, whenever the bond order is 1, 2, 3, we means that we are talking about if the bond order is 1, if it is 2, if it is 3, then we always say that it is a single bond, it is a double bond, and it is a triple bond as given in the classical concept. But the difference between a chemical bond and a bond order and chemical bond. So the basic difference when we are talking about the decimal things, that if the bond order comes out to be 1.5, so bond order and chemical bond, the basic difference in between the two lies here, that chemical bond is always an integral value. The chemical bond is always an integral value, while the bond order can also be in the fraction. It can be fractional value. So it is not the thing when we are talking about single, double, triple bond. If bond order is 1, it is single bond. If bond order is 2, it is double bond. If bond order is 3, it is triple bond. But the chemical bond is always an integral value. Bond order can be the fractional value. Now the third thing, before the diagram we must remember is bond order in terms of bond length. So bond order, the greater the bond order, the shorter is the bond length. Bond order and bond length are inversely related to each other. Higher the bond order, lesser is the bond length. Now the next one, bond order is directly proportional to bond dissociation energy. Higher amount of energy is required when we have to break a triple bond. So bond order is directly proportional to bond dissociation energy. So these are few tips things that we require while we are talking about the molecular orbital diagram and its configuration. And one more, that is the magnetic character. In terms of the magnetic character, we are talking about the diamagnetic and paramagnetic nature of molecules. So we all remember that the paramagnetic are those when we are having the presence of the unpaired electron. If the electrons are paired in a molecule, all the electrons are existing in the form of a pair, then it is considered as diamagnetic molecule. But even if there is a single unpaired electron or some unpaired electron, so in that case, it is considered as paramagnetic in nature. The paramagnetic nature will result in developing of magnetic moment also. So side by side, we can also remember, although it is in class 12, the paramagnetic behavior, that magnetic moment due to the unpaired electrons can be calculated. Magnetic moment can be calculated by the formula under root n plus 2. And the unit of the magnetic moment is Bohr magneton. And what does n represent here? N represent here the number of unpaired electrons. So we will calculate the number of unpaired electrons as present in the paramagnetic substance, putting the value here, and we will calculate the Bohr magneton. Yet that is the magnetic moment of molecule or the ion. So now let us start with the first of the molecule we are talking about, that is the hydrogen, the simplest one. So first, the hydrogen. We will write the number of the electrons present, the type of configuration, sigma, 1s, and the rules followed are same, Aufbau, Pauli's, Hund's, all the rules are same that we have done in case of the filling of atomic orbital. So we get sigma 1s2, but as we have studied in the first one, that whenever we write the sigma, there is always the anti-bonding 1s. But since there are only 2 electrons, so we will be writing sigma 1s2, and in the anti-bonding case, we will be writing as 0. Or if we are not writing, it doesn't matter here. Now, with the writing of the configuration for a molecule, we have to draw the diagram also. How to draw the diagram? Draw the atomic orbitals on the sides and the molecular orbitals in between. The bonding orbital must be having the lower energy and the anti-bonding must be having the higher energy, like this. Drawing of diagram is also a very important part here. This is the atomic orbital, this is atomic orbital, this is the molecular orbital, and the energy will be going from bottom to the top. That is, the energy is increasing. We will write the sign of energy. We will write the energy and the arrow in the upward direction. So in case of hydrogen, we have written the configuration as sigma 1s2. So we will write here as sigma 1s2. There are the 2 electrons present in it, following the Pauli's rule, one upward and one downward. But these 2 electrons can come from 2 different atomic orbitals. So one in this case and the other here. No need to draw any of the electron in the upward case, as it is not having any electron in the anti-bonding case. So 1 is 0. So first we will write the configuration, then we will draw the diagram. Then we will find out whether the molecule is stable or not. So the A point, that the molecule is stable or not, we know that for the stability purpose, the number of bonding electrons must be greater than number of anti-bonding electrons. In this case, the bonding electrons are 2 and there is none in the anti-bonding case. So 2 greater than 0, it means H2 is stable in nature. Now the second case, we will calculate the bond order also. Bond order, the formula of bond order is half number of bonding minus number of anti-bonding. This comes out to be 1, and we know that the bond present in case of hydrogen molecule is a single bond. Then the third thing, the magnetic character. When we are talking about the magnetic character, we know that the configuration is sigma 1s2. We have written the configuration sigma 1s2, and both the electrons in the molecule are present in the paired form. And since electrons are in the paired form, so we will call it, the magnetic behavior is diamagnetic in nature. So the 3 main things that we are required to draw and explain with the diagram are configuration, its stability, the magnetic character, bond order. These are very few very important things that are expected with each of these diagrams. Now let us come to the another molecule, that is the He2. We can also draw for ions also, but now first for He2 molecule. In case of He2, the total number of electrons considered are 4, because one He is having 2, so there are total 4. Sigma 1s2, anti-bonding 1s2, sigma 2s2, and then in this case there are only 4 electrons, so there is no need to write the further configuration. We will write only sigma 1s2 and anti-bonding 1s2. Now after writing of the configuration, what the next step is, we will draw the diagram also. Atomic orbitals in the sides, molecular orbital one lower and the other in the upward part. Okay, now labeling is must. Atomic orbital, and the center one is molecular orbital. Sign of energy from lower to the top part, it is sigma 1s2, and in case of helium, it is anti-bonding 1s2 also. 2 electrons in the molecular orbital, 2 electrons in the anti-bonding also, and from where these 2 electrons have come, the total of 4 at the center, 2 from this atomic orbital and 2 from this. Always remember that the sum of the center must be equally divided into the 2, but in a number S. If there are in the center there are 3, so on one side we will draw 2 and on the other side we will draw 1, because 1.5 cannot be managed. So the other thing now we are followed with whether the molecule is stable or not. In this case, when we are talking, there is number of bonding electrons are 2 electrons and number of anti-bonding are also 2. So number of bonding is equal to anti-bonding. So the molecule is not going to be stable. Hence it is unstable in nature, or we can say that He2 does not exist. Does not exist. Also, we are talking about the bond order. The bond order is equal to half NB minus NAB. Okay, so 2 minus 2, it comes out to be 0. The bond order is 0. So no bond is formed in between the two helium atoms. Now the other thing. Now the other case is of lithium molecule. Let us come to the lithium molecule. Lithium molecule, Li2. The total number of electrons are 6. Writing of the configuration part, sigma 1s2, sigma antibonding 1s2, sigma 2s2, and then antibonding 2s2. We can also write the energy, how the energy is increasing. Okay, now after writing of, in this case, the 2s2 is going to be 0 because total is only 6. We will write the antibonding also if needed, but in this case, it is having the 0 electrons. So, first of all, we will draw the diagram for 1s2, sigma 1s2, the same as we have followed in the previous part. Labeling and writing all should be done very neatly. Then, this is for the same pattern is followed for sigma 2s2. Okay, there is the atomic orbitals, and in the center we will draw the molecular orbital. The sign of energy must be drawn from lower to higher. Then we will write sigma 1s2, antibonding 1s2. In the center there are 4. So we will distribute 2 on this side and 2 on this side. Now, we will also write the configuration sigma 1s2, sigma antibonding 1s2, sigma 2s2, sigma antibonding 2s, but since there is no electron, so we will write the power as 0. Now, sigma 2s2 is having 2 electrons, so we will distribute equally on both the sides, 1 electron on both sides. Now, the other thing what we are supposed to do, after writing the configuration, drawing the diagram, we will calculate whether the molecule is stable or not. We know that the number of bonding electrons are greater than number of antibonding. 4 are bonding and 2 are antibonding. So lithium molecule Li2, the stable case. Now coming to the other part, that is the bond order. The bond order is calculated. Similarly, the bond order is calculated as half 4 minus 2, that is comes out to be 1. The third point, whether it is paramagnetic or diamagnetic. So students, you are able to see that all are having the power as 2. So we will write here as diamagnetic in nature. So these are the few examples that we are talking about dealing with sigma 1s2, antibonding 1s2, sigma 2s2 and antibonding 2s2. Calculation, drawing of diagram. First thing is writing the configuration. Second thing is drawing the diagram, calculating the stability, bond order and diamagnetic character. So these few steps to be followed when we are writing the configuration. In the next video, we will be meeting with the molecular orbital diagrams of the other higher one, that is the nitrogen, oxygen, fluorine. So till then, revise the topic. Goodbye.